I'm Jeremy Jorgensen at Brigham Young University in the School of Family Life, and I'm going to talk today about troubleshooting problems in structural equation models. And the specific problems I'm going to be talking about are sometimes called Haywood cases, where you have a negative variance or a non-positive definite covariance matrix, or a correlation over one or something like that, where there are problems in your model. And so I'm excited to review these today. I've got this little picture, this check engine. This is when you get these warnings in SEM, it's kind of like having the check engine light come on with your car. You don't really know what the problem is, you just know that there's a problem. And sometimes we put it off for a while, or I don't know, it's kind of scary when you get that. You think it's going to cost a lot of money, and we have the same thing when you get this kind of error in SEM where you think this is a big deal, and a lot of times it's actually a small thing that we can fix fairly quickly. But I'm going to talk about how to do that today, how to recognize the problems and then what to do. It's actually pretty common to get these kinds of errors that are sometimes referred to as improper solutions. I gave some of these examples already: non-positive definite covariance matrices, models with a negative variance term, there's a negative psi matrix, correlation greater than 1, models not identified, you need X number of constraints for it to be identified. It's important, if you get this kind of error, to do something about it. You don't just pretend that it's not there, because a lot of times the program will tell you, yeah, your model ran, but you got this error, and it's important to not just report those results because they might be incorrect. To look into this. Let's see, Chen et al. Suggests that the standard errors of the estimates could be affected. These are diagnostic tools. They help us to know that there's a problem, and they can help us to figure out what the problem is. You want to be confident with your results when you submit them for publication, when you present them at a conference. And if you have one of these problems with your model, you can't be confident that the answers are correct. Okay, so I'm going to talk about what are the causes of improper solutions, how do I recognize them, and then how do we fix them. And I've got a few examples here. Oftentimes when my students or colleagues come to me and they say, I've got this message and I don't know what's wrong, then I'll take a look at their model. And whether it's in Amos or M+, I'll take a look at a diagram of their model and try and figure out what is the problem. So can you find the problem with this model? And I'll just pause for a couple of seconds if you want to stop the video and try and find it and then go forward, because I'm not going to wait maybe long enough for you to find it. So for this model, we're missing the one that's associated with this error term regression path, and that needs to be fixed to 1 in order for this model to work. And if that's not fixed to 1, the program will tell you that your model's not identified and you need to impose additional constraints. Well, you can impose as many constraints as you want. It's not going to work unless you impose that constraint, because that's actually necessary for this model to work. Here's another one. Can you find the problem? If you think the problem is that none of the factor loadings are set at 1, you're correct. So probably we would need to constrain this factor loading or one of the others to be 1 for the model to estimate. How about with this model? Sometimes we run into problems when we correlate error terms across a regression path. So if F1 is our independent variable and prosocial behavior is our dependent variable, and we have a regression path, then this is the main storyline that we're looking at. For us to correlate an error term across that regression path oftentimes causes problems. Can you find the problem here? If this is all that's in your model, first of all, it's not identified as a model because you're asking out more information than you're putting into the model. And so anytime you have a latent variable with two indicators, it's going to be unstable. Now you could adjust for that by having other latent variables in the model that could add more pieces of information that can make up for what you don't have here. But note also that neither of the factor loadings is set to 1. And I'll talk a little bit later about a 2-indicator latent variable. There's also something that is suggested by other researchers in that situation. Sometimes we're working with syntax. Can any of you find the problem with this syntax in M+? And by the way, these are all errors that could give you that negative covariance matrix, or the non-positive definite covariance matrix, or a negative variance parameter. All of these could do that. In this case, we're missing a semicolon after GP6. And if we don't have that, then it wants to put GP1 in here. Anyway, it causes a problem. Okay, so what causes improper solutions? Usually, number one, there's a specification error with the model. You're missing a 1 on a factored loading, on a latent variable, an error term. You're correlating across a regression path. You may have excessive error correlations on indicators of a single latent variable. And generally, the rule of thumb is to start with not correlating any of those, and then to improve model fit, you can follow modification indices to correlate some of those. But again, you want parsimony. You want to do as few as possible. You may simply have poor loadings on a latent variable, or you may have omitted paths that should be in a model. So you're assuming that they're 0 by not having them in your model. You may have an under-identified model. You may have a model that does not converge after so many iterations. You may have outliers in your data, and your sample size may be too small for the model you're trying to estimate. You may have problems with missing data patterns, with too much missing, or the patterns of the missing data may be causing problems with the model being estimated. In the literature, sampling fluctuations are brought up, and this has to do with your variability in your variables, but it's somewhat of a difficult term to understand what's being talked about with sampling fluctuations. I'm not sure that I fully understand what that means. 2-indicator latent variables. This includes second-order latent variables if you only have 2 indicators at the second-order level. If you are trying to model a non-normally distributed outcome, like a count outcome or dichotomous or categorical outcome, and you're trying to model it as continuous, you could get this kind of error. Sometimes we see problems when correlating a continuous variable with a dichotomous one. And sometimes we have something called empirical under-identification, where you do have positive degrees of freedom, but there's a problem with your data that's causing a problem, and it could be one of these above problems that I've mentioned. So how do we know if we have an improper solution? Well, in AMOS, we see this on the front. Next to the diagram, under the Manage Models box, we have this little thing that shows up okay if our model estimated, or if it didn't, then we see the 2 X's, which tells us it did not work. When you open the text output in AMOS, if you have a problem, it will take you straight to the message that says the following variances are negative, or this solution is not admissible. You might also see a message like the model is probably unidentified. In order to achieve identifiability, it would probably be necessary to impose one additional constraint. And by the estimates, sometimes instead of having a p-value, you'll have something that says that it's unidentified there. In M+, it might tell you that the model estimation terminated normally, but then go on to say that you have a non-positive definite first-order derivative product matrix, which sounds like, I don't know, what I call the message of death. Like, what in the world does that mean? And the problem is involving parameter 59. You could get a message that's a little simpler that sounds something like this. Modification indices could not be computed. The model may not be identified. Oh, that goes along with the other message there. You may have a negative, it may tell you, M+ may tell you that you have a negative variance estimate. If it does, I suggest you go to the output and look at the variance parameters and see if one of them is actually negative. Find it in your output. Look at correlations. Make sure none of them are bigger than 0. And a lot of times in M+, you'll see the 999 numbers there associated with coefficients. So you'll have your coefficient and then you'll have 999s. And that's okay if you've imposed a constraint on a coefficient. Then it will be there to show you that it didn't actually estimate something because you constrained it to be something. However, if you didn't impose a constraint there, then that's a red flag. Okay, so how do we fix the problem? Well, the first and easiest way is to properly specify your model. And you can do that by looking at your syntax, looking at your diagram. M+ has this great feature now for most models, not some of the more complex ones, but for many models, you can click on diagram and view the diagram after you've run your model, so you can see, what is it that I actually just estimated. Check to make sure in AMOS you might be missing a 1 for a factor loading or 1 on a regression path of an error term. Sometimes AMOS creates what I call ghost variables. These are variables that are somehow in your model, but they're not, you can't see them. Sometimes they may be off the page in terms of, like if you were to zoom in, you might find it out on the periphery. Sometimes when you click on estimate means and intercepts, then if it's a latent variable, ghost variable, then you'll see the 0 show up just somewhere randomly on your screen that doesn't look accounted for. A lot of times when you have these ghost variables, you just have to start over. Like create a new file, rebuild your model that doesn't have this in there. But if you can find it, you can delete it and then your model will run. I have had times where AMOS actually will double correlate variables. Like if I have 2 variables correlated and then I select a bunch of variables and use the plugin to correlate variables, sometimes I'll get a double correlation. Like the 2 variables are correlated twice, and when that happens, the program, it thinks you're really trying to do that, and so it causes a problem. Modification indices will often tell you to correlate things across a regression path, across a structural path that's so from your independent variable to your dependent variable, it'll tell you to correlate errors across those, and that's generally not a good idea. In fact, I can't say that I've ever seen when it was a good idea, but modification indices will tell you that your model fit will improve when you do that, but don't do it. It's not usually appropriate. Sometimes you might be missing a regression path that is statistically significant, an important path in your model, and if you don't have that, you could get this kind of error term. And then you also want to make sure your measurement model is appropriate, that factor loadings are above 0.4, and that error correlations are at a minimum. Again, you start with none because the correlation between items of a latent factor, the correlations between those are captured in the latent variable that they're loading onto. However, sometimes the residual, or what's left over, what's not captured by the latent variable, sometimes that is correlated across items. So what's left over. But I've seen some models where people erroneously automatically correlate every error with every other error in a latent variable, and that can cause some problems. When you have a model with two indicators, Newsom suggests that you constrain the two-factor loadings to be equal, and that buys you a degree of freedom. It also may stabilize your model. When you estimate higher order latent variables or more complex models like common fate models, or let's see, the factor of curves and curve of factor models, things like this where there are specific constraints that have to be placed for the model to be identified, you need to make sure that you do that, and otherwise you're going to run into these kinds of problems. Okay, so how do we fix these problems? Some more suggestions. Using a larger sample. Sometimes the problem is that you're trying to estimate a model that's too big for the sample size that you have. This is really common, actually, where I'll have somebody come in with a model and they can't get it to run, or they come up with these negative variance problems, and I'll say, okay, how many people are in your sample? They'll tell me, well, I've got 100 people in my sample. Okay, well, how many parameters are you trying to estimate? And using the NQ rule, usually you should have 10 people in your sample for every parameter, and that's the minimum. Actually, a lot of people say you should have 20 people in your sample for every parameter that's estimated. So if you're estimating 77 parameters, then you should, 44 parameters, then you should have 440 in your sample to be able to estimate that on a minimum. There is a quick check rule where usually you don't have to have that many to estimate your model, but you do need to have 10 people in your sample for every observed variable in your model. So if I have 30 observed variables in my model, then I should have 300 plus people in my sample. And when you start to push that ratio to below 10 to 1, then you increase your likelihood of having a difficult error that you're not quite sure what to do with. If it looks like your model's specified correctly, but you still are getting these error messages, it's time to start looking at your data. And a lot of times the problem is extreme outliers, a lot of missing data, data entry errors where you'll have a scale of 1 to 5 and somebody's got a 300, a value of 300 or something like that. These can be problems. Maybe you have an outcome variable that's not normally distributed and you're assuming that it's normally distributed. And sometimes, especially using M+, let's say you're doing your data manipulation in SPSS and then you bring the data into M+, a lot of times the data can get corrupted or the columns of data can get shifted off by one somehow in that transfer. So you might want to check, and the way to figure this out is to run some frequencies in whatever program you're using, like SPSS, and then run the basic analysis in M+, and see if you're getting the same means and standard deviations. You can look at the data file that you've transferred over and see if you see any problems. Sometimes that's a problem. I mentioned categorical or non-normally distributed dependent variables as continuous. AMOS doesn't handle dichotomous count or zero inflated outcomes. You may be able to use a categorical or dichotomous outcome using a Bayesian approach in AMOS, but I'm not sure that you can do that actually. M+ does handle them well, but you have to specify that the distribution that you have, like categorical or count or zero inflated, something like that. And you also, even if you specify that a variable is categorical, if you have very small cell sizes, like let's say one of your categories has very few people, that may be the reason why you're running into this. I've seen this with ordered categorical variables. Let's say you have a Likert scale of 1 to 3, and you have most of the people in your sample in 2 and 3, and in category 1 you have just a small amount, like 5 or 6 people or something like that, then that can be a problem as well when you specify those as categorical. If your model doesn't converge, so the models that we run in SEM are oftentimes iterative, and where the computer program is iterating and trying to get to the best solution possible. And sometimes the model doesn't get to those best estimates within the number of iterations that are specified, or the default. And the default, I believe in M+ is 50. It actually might be less than that, it might be 20. At any rate, you can increase iterations, and if you increase iterations up to 500 or 5,000 or 50,000, if there's a problem with your model, usually the model, it will stop iterating before you reach that number, and it will still tell you that you've got a problem. And then you know that you've got a problem with your model, that it's not something going on behind the scenes with number of iterations. There are a number of atypical solutions. Sometimes you may not have good start values. Amos and M+, they automatically provide start values for your model. And I always think, how in the world would I know if I have poor start values? Well, you can't know. There's no way of knowing. But if you tried everything else, you could run a regression with your data in a regular program, get those estimates, and then plug those in as start values. Chances are those are going to be closer to the actual values in your model than whatever the default is, say 0 in M+ or Amos. So that may be one thing that you can do. Let's see. You really don't know the distribution of your variables. It's, you know, unfortunately, these problems oftentimes come up in very complex models. And if you haven't done your basic work of looking at distributions, knowing your data really well, then you could easily get to a major problem here down the line and find out, okay, one of my variables isn't loading well on a factor, or I've got a bunch of missing data that I didn't know about, or there's a data entry error, or a non-normally distributed variable. And so it's important to do that work up front with these models. Occasionally, like let's say your model is estimated appropriately, you've looked at your data, you can't find the problem, M+ gives you this technical output. A lot of times it will say, the program will say, you have a non-positive definite covariance matrix. The problem involves parameter number 16, for example. And then you could ask for the Tech1 output, and you could go down to it and look at which is parameter 16. And you could use this little Greek alphabet coding to say, okay, number 16 happens to be in the lambda matrix, so then I could see, okay, it must be one of the factored loadings, and so then I know what the problem is. You can go and look at, see what variable it's associated with, and go in and look at the data for a specific variable. So this can be really helpful when there is a problem with your data in finding out what that problem is. I will say that most of the time, this parameter that it tells you that's the problem, most of the time that is a decoy. That's not actually the problem. And the problem actually has to do with your model not being specified correctly. And so the thing to do is to go and check your model and make sure you specify it correctly, so you don't do all this work only to find out that parameter number 16 involving whatever variable is really not a problem. So these are examples of the message of death, what it might look like. Model estimation terminated normally. This, by the way, this is a model that involved 56 cases. There was a non-positive definite first-order derivative product matrix. The problem involved parameter 31. Really, this is most likely due to having more parameters than the sample size in one of the groups permits. So if you have a sample of 56 and you're doing a multiple group analysis, chances are you're going to run into not having enough sample size. Another warning, residual covariance matrix theta in group grad is not positive definite. This could indicate a negative variance residual variance or an observed variable, correlation greater or equal to 1. Anyway, could be a problem with variable DE4. Again, look at your model first, and then once you've exhausted everything else, look at your syntax, make sure you're not missing a semicolon. Then you might go and look at parameter DE4 or that variable and see what's going on with it. If your model's specified correctly, you've checked your data, you've got a large enough sample, you don't have outliers, your variables aren't not normally distributed, and you have positive degrees of freedom, then maybe you could look into some of these more complex solutions that you'll find in the literature. And I'm not going to actually show you how to do these because I can't say that I've ever seen that these were the solution. Usually the solution is that there's just a problem with the data model being specified. And I guess I've been teaching an SEM class now. I think it's 4 years, but involved with the class for a couple years in addition to that. I just have never seen where someone actually had to do these things. But you could look and check the confidence interval, see from the standard errors and see if it includes a 0. You could calculate the Z, and you could do a Wald test. You could do this likelihood ratio test statistic. You could check the Lagrange multiplier. You could use a bootstrap resampling method. Use a scaled chi-square difference test, signed root tests, empirical sandwich estimators. These are all just complex ways of looking more in your data. And if you're going to do one of these, you want to make sure you really understand the process or talk with an expert that can help walk you through it, make sure you do it correctly. In summary, here's 2 decision trees that are published, one by Chen and one by Newsom. They suggest, first, is your model identified? If so, do you have any negative error variances? If so, do you have any outliers that are a problem? If not, is the model empirically under-identified? If not, do you have sampling fluctuations? If so, constrain the negative variance to be 0, a small positive number, or to be the population variance. I'm really hesitant to constrain negative variances to be a 0. I think that can be done, especially if they're close to 0, and you see that more commonly done in situations with growth mixture approaches or mixture where you constrain the variance within a given mixture group to be 0. But in general, I would say I would steer you away from doing that. Newsom suggests careful specification, use larger samples, model factors with 3 or more indicators, use reliable measures with higher loadings, and use well-conditioned data. I think you avoid a lot of problems doing that. Here's my decision tree. Adjust your specification so it's correct. Consider potential problems with 2 indicator latent variables. Increase iterations if needed for convergence. Check your data. If that doesn't solve the problem, then check your data. Look at sample size, outliers, categorical count outcomes, or very different variance parameters. I don't think I talked about that much today, but sometimes you have a variable that has a variance that's small. Let's say you have a range of 1 to 5 in one of your variables in your model, and another variable like income has a range of 0 to 200,000. So you can see that the variance parameters aren't going to match on these, and sometimes that causes a problem. And so you might want to rescale your income variable. If none of these things work, then you might change start values, run tests of sampling fluctuations, consider fixing a negative variance to 0. Again, I would say avoid that if you can. And here are some references that you can look at. I hope you get to a point where you feel comfortable addressing these error messages that can be very distressing, much like the check engine light in your vehicle. So good luck with your data. Thank you very much.